Hello, I'm Robert. Welcome to my channel where I fact check things that scare you. And this time I'm just going to talk about vaccines and about why the Pfizer and Moderna vaccines were so effective. And it's a really interesting detail, but it shows how we are using science to get ahead of the virus. And this is a tweak that is only used for those two vaccines. Well, it's not being used for AstraZeneca. And AstraZeneca will be able to be more effective once it is able to do this. And so this shows the SARS-CoV, you've heard of the protein spike. And this shows the spike as it is before it enters the cell. And this is what it looks like as it starts to enter the cell. It fuses with the human cell on its way in. As you can see, this is quite a bit fatter. And so what it turned out that some vaccines were not being very effective because the vaccines were presenting the body with this long thin spike. And so it developed the antibodies, and this is your adaptive immune response that develops quite a while after you've been infected, and it also develops about 10 days after you've got your vaccine. And so your body develops the response to kind of clog up this version of the spike. And it doesn't work so well with this version of the spike. So the viruses were still infecting the cells, some of them. So this, anyway, yeah, so the question was, can we stop the virus from going like that, the vaccine from looking like that, and make it so the vaccine looks like that? And so what they did is they added these little, and this is the Hexapro variation. I don't have a diagram of the 2p variation, which is just 2 proteins. This has 6 proteins. But it's got these little red sphere things, red and blue sphere things. And the original 2p one, then 2p, 2 proteins one, it just had a little bit of rigidity and it stuck it in this kind of broad shape instead of the thin shape. But it only works with some of the spikes. So if you do this, then only some of the spikes end up being the right shape. And so then if you do the Hexapro variation, it turns out that 10 times as many of the spikes are the right shape and are stable. So this is not yet in any current vaccine. It's being tested, this new variation. This then is a possible second or third generation vaccine. It's if they expect it to be more effective, to generate a stronger response, and to be much more stable. And this variation, they tested it, then it is able to withstand 50 degrees centigrade of heating and 3 freeze heat cycles, and it can be stored in room temperature for at least several days. So this is a big step forward from especially Pfizer, which needs to be kept at ultra cold, dry ice temperatures. And it's the same also with Moderna. Even that is nowhere near this level of stability. So that's coming in the future. Things like that. You can't say for certain, it's still being tested, but it's very promising. And this definitely works. It already works. The 2p, the 2 protein variation, that is already being used in Pfizer and in Moderna, and other vaccines can try that out as well. And there are many other ways that the vaccines can become more effective. First of all, I'm just going to show this. There's the bit about it's at a 9.8 factor in higher expression. And then I've got another image here somewhere. After 3 cycles of freeze thaw, 2 days of incubation at room temperature, or 30 minutes at 55 degrees centigrade. Was there anything else? Was that all that I took a screenshot of? That retains the prefusion, that is just the abstract, I think. Can also withstand heating and freezing. It's likely to be useful in the development of vaccines and diagnostics. So that's one thing. So one of the ways we can expect second and third generation vaccines to be better. And so I just want to talk a little bit about some of the other ways. I just did another video where I went on and on as I did. I talked about all sorts of different things, but I'm doing a shorter version now where I'm not going to go into all that. But I just want to talk a little bit about some of the other things. So about other ways that vaccines will be improved, and I'll just keep to that topic instead of digressing. So first of all, one of the discoveries with the AstraZeneca is that keeping a longer distance between the two vaccine doses leads to, it dips down a little bit in between, but it stays at a very high level compared with Pfizer. It's well above 50% all the way to 12 weeks. And then at 12, and it's 85% or something quite early on. I've had it just a few weeks ago, so I'd be at 85% probably by now, and just for one dose. And then the second dose at 12 weeks, then that one then, if it's delayed to 12 weeks instead of having it 4 weeks, then that boosts your immune response, and it's much stronger after 12 weeks than it would be if your second dose was at 4 weeks. And it also is likely to last longer if you do it at 12 weeks. And the reason is that because it's actually very unusual to have two doses so close together. With most vaccines, it's 2 months or 3 months, or you have a boost after a year and so on. But even for the ones where it's very close together, 2 months is about the minimum. And so it's not really too surprising that it's really better vaccinating after 3 months. And the technical reason is that after you first of all you develop are these antibodies that stick onto the spike or what other bits of the virus and stop it infecting you. And then but then later on you then develop these B cells, which are the memory cells. They remember the response and they help your body to generate the antibodies quickly, if I understand right. Anyway, it's the B cells. Do correct me if I got it wrong, but it's, yeah, I think that's it. And then because you also have other cells as well that attack the cells, and then you have these cells that kind of reinforce the antibodies. Anyway, these B cells, they first of all you have the antibodies, then you have the cells that remember them. So if you give your second dose later on, then your body starts to create the B cells, and so the second dose tells your body, okay, you've really got to remember this, because here's the virus again. Not really the virus, it's a vaccine, but here's the thing that you're protecting yourself against again. So it then triggers the B cells, so then you get a stronger immune response because you've got more of these B cells, and then you've got a longer term, you probably, they don't know, have a longer term memory of it as well, a more lasting immune response. So it might be that in the future we have them spaced further apart. Another thing that might happen in the future is already being tested. This works with other vaccines, and that is that once you've got more than one vaccine for the same disease, it often creates a much stronger response to have the booster shot or the second dose with a different vaccine. And the reason there is that your body develops an antibody response not just to the spike, but also to the delivery vehicle, which in this case, for instance with AstraZeneca, it's an adenovirus. And possibly the reason that Pfizer works so well is because they've got a delivery vehicle that you don't get these kind of immune responses to so easily. And so with the AstraZeneca and the adenovirus, which is a cold virus from chimps, and so it can't replicate in humans. And that's what's used to deliver the AstraZeneca vaccine, to deliver the spikes, or deliver the DNA that then makes messenger RNA, which then makes the spikes in your body. And because it's a DNA called virus that can't replicate in humans. And so it delivers a little bit of DNA into the nucleus of your cells, which then makes the messenger RNA, which then makes the spikes. But it can't replicate itself, so that's the end of the process. It just makes lots of spikes. Whereas Pfizer and Moderna, they deliver the messenger RNA itself, packaged into a little package, so it bypasses that whole bit of injecting a little bit of DNA into the nucleus of the cell. That just doesn't do that with the Pfizer and Moderna. Much cleaner vaccine. But they're both body's completely rid of both of them after just 10 days or something, a few weeks, a week or two. So with this, what happens then is that your body will develop antibodies, not just to the spike, which the adenovirus, remember, hasn't got this spike when it enters the cell. It enters the cell and it's got a little bit of DNA inside it, which causes it to create the spike, create messenger RNA, which then creates the spike, which then is expelled from your cell. And then other cells then will see that spike. And the spike can't do anything. It can't actually enter into and replicate because it's got no RNA or DNA in it. So the spikes just then get mopped up and your body develops antibodies to the spikes. So your body, the unfortunate thing is that your body will see the adenovirus entering the cells and look at the adenovirus and say, oh, that's an attacker. And so it'll develop antibodies against the adenovirus, which then stops the adenovirus in the second boost from getting into the cells. And then that just blockades the whole thing. Because if the adenovirus can't get into the nuclear cell, can't inject its DNA into the nucleus, then no spikes are made. And so there's nothing to develop an antibody response. So it may be that is partly why it helps to have 12 weeks in between, as well as the B cell thing, also maybe for getting a little bit of this immune response, antibody response. Anyway, whatever the reason, then this means that if we could get, for instance, the Sputnik V vaccine from Russia, that is also developed based on a cold virus, an adenovirus, not the coronavirus cold and our adenovirus colds. This is an adenovirus cold. And the Russian one is based on a human adenovirus, and they then have modified that in order to inject the spikes. The rest of it is just the same as for the AstraZeneca one. So you would do your second dose based on the Russian one, and your first dose based on the Oxford one. And then if you and you could either do it that way or the other way around. I think this is being in trials. Then another thing you can do is first dose based on AstraZeneca, second is the Pfizer. Then first the Pfizer, second is the AstraZeneca. And the hope is that this will be more effective than either Pfizer or AstraZeneca separately. And that's entirely possible. And so we could have the second generation Pfizer Moderna. We've got lots and lots of different vaccines coming along. Very many different ways. And so we've got lots of mix and match. Any of the vaccines could be mixed and matched with any of the others. And any of those combinations might end up with something that is actually better than either of them individually. Then you've also got the science behind it, which I talked about with this. There are all sorts of things going on by way of developing the science of the vaccines as well. And that's why the World Health Organization talk about this as the first generation vaccines. And they're amazingly effective already. But the Pfizer is able to stop 94% of even asymptomatic cases. So that means stopping 94% of transmission of the B117 variant. If we can manage to stop the variants from arising, new variants from arising, and restrict the existing ones. And the best way to do that is just reduce cases down, down, down. The variants arise in regions with lots of community spread. It's no coincidence that the main variants have arisen in the United Kingdom, in Brazil, and South Africa. Those are all countries with lots of community spread and able to detect the variants. Now, the WHO are pretty certain there are other variants that have not been detected in other countries with intense community spread, but just aren't able to detect them. And the first one was discovered in the United Kingdom because we had the combination of lots of community spread and then also very, very high capability for sequencing the virus. We had the most. In fact, I don't know if it's still the case, but it used to be that we had more sequencing going on in the United Kingdom than the rest of the world put together of the virus. So a very high percentage of the cases were being sequenced, so that's why we found the B117 variant. It was first identified in the United Kingdom. It could have originated anywhere, but it could very well have originated in the United Kingdom because we had such intense community spread here. But anyway, it could have originated some other country, and then it's very unusual, these variants, because they probably, I just very quickly say this, but you may know this already. The variants suddenly develop maybe half a dozen modifications all in one go. They probably arise in someone who is immunocompromised, who has had the disease for weeks, months, and then they infect someone else. Because it seems to just suddenly arise in one go. It's almost certainly the B117 variant originated in one particular person, and then the P2 variant in Brazil, probably the same thing, and the B1 whatever it is, that I can't remember the number now, the one in South Africa, so that would be another person there, just one individual person. Now, it's not that particular person was responsible, because it would have arisen eventually with that amount of community spread, but that's how it happens. If you've got lots and lots of community spread, then you'll have someone, just a very rare example of someone which just simmers along in their body, and it gradually develops more and more variations, and then they infect someone else eventually. So that's so if we can reduce the community spread, reduce the cases per day, then this won't happen anymore. And if we could get down to, say, New Zealand, China levels of cases per day, you're not going to get a New Zealand variant, a variant that originated in New Zealand, or one in Australia, or one originates in China. It's no coincidence that it happens in the United Kingdom, and there's now some being identified in the United States who have almost certainly they've been there all along, they've just been discovered. So far, I think none of the ones in the United States are variants of concern. Just these three at the moment. But that's why we have to keep cases way, way down. And we are definitely we're going to get ahead of this. We've got just fantastic science here. And we've got these therapeutics coming along as well that are going to help people. So as the World Health Organization say quite clearly, we've got the light at the end of the tunnel. So we're in a dark tunnel at the moment, but we can see a glimmer of light at the end. And then we know we're going to get out of it, but we're not quite sure how long the tunnel is. But we can, it's not a very good metaphor because once you start saying this, but we can get out of it much faster if we can reduce, maybe we've got a faster train or something, we can get out of this tunnel much faster if we can keep the cases low so the variants don't develop. And if we keep on doing everything, and so and that's one of the things where I went on with the longer video. But most of you who have watched this will have already heard we're talking about, to it everything about the need to isolate away from your own household if you are a case or if you are a contact. Then most of the transmission is in households. If only we could do that, just that one thing. And sadly, even now in the United Kingdom, United States, most people don't know that one of the most effective things you can do, and if you are a case, then isolate away from your own household as soon as you get symptoms. Your own household are the ones who are most at risk from you. And they almost certainly don't have it yet, even if you develop COVID. Even though they say you're most infectious in the first couple of days before symptoms. But the infectious period continues for a long time, and this disease spreads through very rare super spreader events. 9 times out of 10, even 2 people in a couple will not give it to each other. And then in that 1 in 10 case, then one person will give it to not just their spouse or their partner, but to a whole group, a party say. It often happens in a group of a crowd of people getting together, all very close, shouting, singing, stuff like that. So that's why it's very commonly, it spreads very quickly to lots of people all in one go. I don't think they quite understand why it happens like that, but that's how it works. And so if that super spreader event hasn't happened yet in your house, even if it's 2 of you in your couple, then almost certainly you haven't been infected yet. So if you can isolate straight away at that point, even as soon as you get sick, then very likely you've protected your own household. And then if you are a contact of someone who is a case, then it's got a very long incubation period. Lots of people think, oh, I've tested negative. They think like flu. It's not flu. It's a very different disease. It's not related to flu. And if you have been in contact with someone, then for the next 3 days, typically, and it can be quicker than that, and it can be up to 14 days, then you will test negative every day. And you're not infectious for day 1, for day 2, for day 3, and then day 4, that's when you're still not tested, you're still not getting symptoms, that's when you're infectious. If you were tested, you might test positive. Day 4, then you very probably would test positive. Day 5, then you have symptoms. If you take an average case, and it's day 4 and 5, that's when you're going to start being infectious. And so you've got those 3 days, 3 clear days. Just an average case, sometimes it's faster. And that's why contact tracing works so well for this disease. It doesn't for flu, where it's much shorter. So if you are a contact of someone who has COVID, then you should isolate, quarantine away from the rest of your household with as best as you possibly can. And so if we can manage to get the cases way down to just a few per day, then the most effective way that our governments could actually stop it at that point would be to really explain what I just explained, so hardly anyone knows that. Then offer accommodation in a good hotel. Say you're going to take the dogs for a walk, feed their cats. You're going to all the food is free, the Wi-Fi, a reasonable hotel, not a shoddy hotel. A place that people will want to go, and it's all totally free. If you can do that, and then encourage people and say, now if you go to our COVID isolation hotels or our quarantine hotels, if you're a contact, then you get all this for free. Everything is done for you. You continue to get all your work, your pay, you get your payment, your salary will be paid for you. So if you're missing work, and all that done for you. If we could support people 100% and make it like it's like you've almost you're you're on a cruise line or something, except sadly, of course, you just got to stay in a hotel for 14 days. All very boring, but you give them Wi-Fi and free Wi-Fi, free download of anything, free ultra fast broadband if you can manage that, all that sort of thing, anything that could make it easier for them. Then that would be the most effective way of getting it down. Once you got to that point, not fine them, not say you've got £100 if you've got to pay £1,000 or whatever. That's not the way to do it. You've got to use the carrot here, explain it. They will want to do it. If you support them and if you explain it properly, that this is how you protect your household, they will want to do it. And so anyway, and then I think we get near 100% accept, 100% take up of an offer like that. And once you've got only a half dozen cases a day, say, then they should all be staying even in the best hotels, whatever you can do to encourage them to isolate away from their own household. And this would be, the World Health Organization used to say that with every press briefing. And towards the end of last year, Mike Ryan said that was his golden wish for us to do that. But very sadly, they've gradually stopped saying that. I think they just find that nobody's listening. They just touch on it very, very slightly. So it's so sad. But that was the key for the Chinese in January, February 2020. And that is how to stop COVID. Most important of all. Anyway, I'm sorry, I didn't mean to talk about that. Now I have. Oh well, I'll upload this. It's a little bit shorter than the last one. And then, yes, I don't think I'll try another one. I'll just upload this and then hopefully it helps.